Thank you for a wonderful introduction. It's interesting to be back actually in this room talking. So, I was actually here a few weeks ago, but it's interesting to actually be here with lots of students here. And I appreciate the opportunity to be able to talk a little bit about our program, as well as I'll talk about some research that was actually done here by someone who'll be graduating in a month. Maybe, right? Is that how that works at this stage? No, pretty much, okay, good, thanks, I appreciate that. So, and then I'll also talk about some research that's been done predominantly by undergraduates in our lab in Belleville. So, without further ado, here's a little bit about me. So what's kind of interesting here is we actually had our water working in our lab in Belleville and it wasn't working in Edwardsville. So one of the analytical labs needed water, so they came down to our lab and they have since highlighted the fact that I provided high quality H2O, like some people in a movie. Some things about me, I ride my bike a little bit, so I actually have my gear in my bag because I have a ride at 5:30 that I have to run in Wentzville. This is me. I actually, when I left here, I had about 6 weeks of do nothing time. So I trained to ride a 200-mile ride in one day. So I've done this 2 years in a row on the summer solstice, to where I raised money for people who suffered through human trafficking. And so I just signed up for that again. I don't know why. So, but I am going to continue. Thank you. Let's see, I guess from here, this just highlights the fact that I spent a little bit of time in New York City. My students in SIUE had a pajama day and didn't tell me about it, so I made my own self-proclaimed pajama day. And that's me outside an office, just highlighting that fact. Before I left here, my instrumental and forensics class gave me some parting gifts. So I got the Teachers Are a Force for Evil card. And they signed and said all wonderful things about it. So there's lots of 4-letter words in there, but that's okay. So, because I'm a mean and nasty professor, I'm the meanest and the nastiest that there is. So just something to keep in mind, and then
the world is a band.
So my question for you is, who sings this song? No. There's a band. What band sings this? Yes! Which is in reference to blowing on pumpkins, which is what I did on campus. So we have to let Dr. Ulrich know that we did this because this was mainly for her. Okay. So forensic science is usually shortened to forensics. It's the application of, I walk around, by the way, I don't like to stand in the front of the room, so that way you don't fall asleep. Because that way I get to throw things at you, I throw things at students when they fall asleep, right? So those of you that have had me for a class, that's true, correct? It's usually the heavy plastic erasers, not the soft ones, it was the ones that would really hurt. So that's what I was usually targeted with, so. Don't tell my previous assistant dean or associate dean that, okay?
She's not listening anything.
Good. All right, so forensics is the application of a broad spectrum of sciences to answer questions of interest to a legal system. So that's something we need to keep in mind. What do you need to think about as a forensic scientist? You have to think about all the different aspects from when a potential crime was committed all the way through a trial. So you have to be able to think about how the evidence was collected. Was it collected in a way that there was no bias that was entered in, that it wasn't contaminated? In a lab, the evidence needs to be pieced together to answer the question whether or not someone was guilty or innocent. And that's usually done in a legal proceeding. As a forensic scientist, tracking that is important. So you have to track when evidence is collected. You have to maintain chain of custody, even when you're doing your analysis. So what's kind of cool here is I actually have a picture of a former student from Maryville. So he's actually doing some gel electrophoresis work, and I actually have this here because we can talk about how the separation occurs, but more or less, we can summarize. You have a charged particle, you apply a potential, the bigger particles move faster or slower? Slower. So if we had to look at this plot. Up here, are the bigger particles here or the bigger particles here, if your starting point was here? The bigger particles are closer to that starting point, right? So that's something that you need, or the bigger ions, I would say technically. So that's more or less what happens with electrophoresis in regards to your separation. You use the charge to have the separation or make the separation occur. And then you're able to identify the bands that occur based on how far they migrate. So there's different factors that you have to take in terms of being able to migrate through the gel. What's kind of neat though is separation systems today, you don't need the gel, so you can actually use catheter electrophoresis. And so this is actually a sequencer that we have in our lab. And what will end up happening is we can actually put a sample in here, and then it gets pulled up into here, and then you make your measurement here. This is actually where the measurement occurs. So with the 4 different capillaries, so I actually zoomed in on that cartridge. So those cartridges are actually, I messed up. So we actually have our sample pulled up through here. So I was focused in on here. So our sample is actually pulled up through here. The sample travels through the capillary, and then you can make your measurement. And our measurement is done via fluorescence. So you have to use a fluorescence tag, right? Did you learn about tags? Those of you that have done any work with DNA. You might not all have seen that yet. All right, next, some other things that we actually have in our lab. So we actually have a GC mass spec. This is very similar to the Agilent system that you have downstairs in your lab. Ours is Shimatsu. We also have a dual channel GC with flame ionization detection, which allows us to be able to do ethanol quantitation in blood. So we can do BAC. So we teach people how to do that. We also have an HPLC similar to what you have that is running right now, I think, as we speak in your instrument room, because I heard the gears churning on the pump as I walked by the lab, because I'm very familiar with that sound because I'm the one that helped instigate that purchase. So what's kind of neat about all these particular systems, you can actually use them to identify potential illegal drugs, purity levels of the drugs, a lot of different factors there. It's nice to be able to identify whether or not you have GHB, methamphetamine, cocaine. We typically work with derivatives of those. We won't necessarily work with cocaine per se, but we teach you the methods that you need to be able to do that in a safe manner. Here we actually have a microscope. So this is actually an FTIR Raman microscope. So if I pop this little cover down, this functions as a microscope, and it's attached to a Raman spectrometer, and then it's also attached to this IR spectrometer that is here. So it allows us to either do Raman measurements or FTIR measurements on samples as small as 7 microns in diameter. So the latest thing that we've actually been able to do is in our lab, we've actually had a graduate student analyze and identify sperm. So they've been able to quantify sperm samples based on Raman scattering that occurs. So we're working with Shimatsu now to be able to publish that as an application note on our page. Let's see. So I'll talk about how to use our current FTIR. I think my batteries are starting to die, but we'll see. So we're using our current FTIR to analyze for adulterants in beverages. So on the right, we actually have a comparison microscope. We actually have a Leica microscope that we spent about $100,000 on to be able to do the comparison of ballistics. So you can work with shell pastes pretty easily, and you can match based on a comparison pretty readily. What's nice about this is in our lab, about 50 feet away, the Illinois State Police Crime Lab actually has a training facility for ballistics. So when they have to train people for their lab, they all come down to Belleville and they hang out for about a year and they do their training in Belleville. And when I actually started, they actually had a training class going on. And one of our 2 graduates from our first class ever applied for a ballistics position at the Indiana State Police Crime Lab. And they got spun up by the lead trainer from Illinois State Police Crime Lab, so they spent about 10 hours working with them. They walked in on a Monday for an interview, got a job offer on a Wednesday, which is absolutely unheard of for any government position. Usually it takes 4 to 6 weeks minimum. But she did such a good job in terms of the interview, they didn't want to lose her. So they figured out a way to streamline to make certain they could make her a job offer. So we were very fortunate in terms of our interaction with the Illinois State Police Lab. And I've been actually very fortunate. I know most of the directors of the crime labs within the St. Louis metro region as well. So I've worked with them quite a bit in St. Louis metro in particular. I've also worked with St. Charles County. I've worked with St. Louis County. So I've been very fortunate to build these relationships with all these labs, state labs, Illinois, Indiana. I also have worked with Missouri State Highway Patrol. Some of the graduates from Maryville have actually gone on and worked through the Missouri State Highway Patrol system and actually moved on to other positions just because they found other positions that were a little bit better for them. I talked about FTIR, so I'm just going to move on a little bit here. This is my favorite instrument. To answer your question. So not the
He
piano.
said piano to me earlier. He said piano was his favorite.
So, this is an inductively coupled plasma, so I actually have this in the lab. The one that I actually have, I got donated from the Library of Congress. So, I don't have it set up yet though, and I'm waiting for a ventilation system to be installed. It's kind of a sticky subject right now, but I'm working on it. In my copious free time, I'll be able to get it done. But the goal here is I'm gonna be able to analyze for different metal contents and trace metal contents in bullets to be able to match bullets and casings to a particular box that has been found, for example. It's something that we can do fairly easily. There are other techniques that we can actually use. We actually have X-ray fluorescence. We have a benchtop unit, which is similar to the handheld unit that you all have here. Except the one that I have in our lab currently is about 100 times more sensitive just because of the intensity of the X-ray, but it's the disadvantage is I can't take it out of my lab. All right, so careers in forensic science. You're just stuck doing one thing. So you're just stuck working in a lab. There's nothing else you can do. Right? Okay, good, thank you. So those of you that know me, I'm very interactive, right? So there's a lot of different things that you can do. You're not just limited to working in a lab, either in biological sciences or in chemistry. So you can go anthropology, criminalistics, odontology. I don't know what that is. What's odontology? Teach. Pathology, actually a former Maryville student who was actually athlete of the year. I think it was 2014. So yeah, a long time ago. Was a forensic science major. She ended up having to leave for different reasons, but she is actually a pathologist in North Carolina. I gave a presentation at the same conference. She gave a presentation this past February, so we met and chatted. It was great. She's doing great things. This is a long pathway, but it's something that people could do. She's a medical doctor. She's actually she's a DO. She's doing great things. So she's going to be running a lab. She's going to be working as a medical examiner probably within the next 2 or 3 years. Toxicology, trace chemistry, that's more chemistry focused. I don't specifically have DNA listed up here, but DNA is something to keep in mind. Digital and multimedia science, that's huge. That's where the money is right now, quite honestly. Because there's so much that's going on in terms of technology and this little thing called AI, which we will be using later. So, can you handle that? So you all have your phones out, so you're all text your friends and pretend that you're looking something up, right? Okay, so where do I want to work? You have a lot of different options here. For all the work, for all the crime lab work, so if you're gonna work specifically in a crime lab, you need a degree in biology, chemistry, or forensic science. I'd say probably 15 to 20% of our applicants have a degree in criminology or forensic psychology. And you don't have the science background that you need to be able to get the master's degree. Okay, so if you're looking at going to work in a crime lab specifically, those are the areas that you want to focus in. So the MS degree is required to be a technical leader. So that's Caitlin, who is actually working in the Illinois State Police Crime Lab, and I don't know who she's standing next to, some weird guy. But I mean, that's pretty much how that works. At the Belleville campus, we do fun things on occasion. So, this kind of highlights some of the things that we're doing. We're building a strong program. Our lab is BSL2 certified. We actually have a course that's focused on human DNA analysis. You have a lab, you actually work on samples, blood, semen, you analyze for DNA. You have to match it to a sample to see whether or not it does match or not. And we do make it difficult because we do have family members involved. So we have similar families intentional to help you identify the differences. It's not an easy class, but you learn what you need to learn to be successful in working in a crime lab. And DNA is probably where it's currently, you currently have the biggest backlog, so that's something to at least keep in mind. We do quite a bit of outreach. We do a murder trial course in the summer. So we actually will be working with 36 high school students. We have over 65 students apply for this currently, and I think it's probably going to go up, but we only have 36 slots. I mentioned all the collaboration that we have. We're working towards feedback accreditation for our program. We're probably going to start the application process next March. Once I know a little bit more about our faculty situation, because I'm probably going to be looking to hire at least 1 or 2 people. So, and lastly, hopefully we'll add a new DNA lab. The way we have our lab set up currently, we have the DNA set up throughout our entire lab, and the likelihood for contamination goes up greatly. So, and what we're looking at is designing a lab to where we can actually utilize it for outreach, to where people can look in and see the different processes that occur in terms of extracting a sample, amplifying the fragments, making lots and lots of copies, right? Those of you that have done any DNA work at all, we use a photocopy machine, right? That's what our DNA person told me, but she told me, you know, you're a chemist, we have to explain it in a way that you can understand it. Some things that you want to keep in mind here, these are the courses that you need to be able to take if you are going to ever apply for a forensics program, and it's not just our program. I've heard horrible things about this course here. So, you know, but I've heard horrible things about people that teach it too. Make certain, I say, out of all of these, the things that you want to do is try and take these sooner rather than later. Okay, so try and take them, make certain that you take them while you're going towards a degree, if you have any interest in forensics at all. Here's Allison, so she's my first student, she'll be graduating in May or August. And I think I've kind of highlighted the different things that I talked about here. Our lab is truly state of the art. We have all the instrumentation, and I'm getting more of the instrumentation that you need. I'd say yearly, so hopefully I'll be able to spend another $200,000 or so this upcoming May and buy a little bit more to make the lab function. We are very well supplied in terms of what you need to do the research with. And with that, do you have any questions about the program? No one here wants to do forensics, right? I mean, you're all people going to optometry school. Everyone's going to optometry. Okay. Y'all just show us that path, right? It's not like I know that or anything like that. Okay, so research. I'm going to talk a little bit about it yesterday. So I'm going to talk about herbicide detection in water runoff for golf courses. And I'm going to have you help me because I need to utilize your knowledge in terms of what you've learned in your lifetime. So just so I get a little bit of background here, who has taken at least Gen Chem 2? General Chemistry 2, good. Who has taken quantitative analysis? Yes! 1, 2. Cool. And then who's taken physical chemistry? Yes! Good. If you haven't taken any of those courses, that's fine too, but we'll be fine. Okay. And then I'll also talk about research that's happening currently in the lab. I say a little bit of tomorrow because it's ongoing. Using ATR, FTR, which you also have, those of you that have taken organic, so you know a little bit about that, right? Yeah. All right, so herbicide detection and quantitation of water runoff. You might be familiar with this map. Anyone recognize this map at all? Anyone know where we are? So right now, I think we're about right here ish. Okay, pretty close. So these are golf courses that are in the area. And what we did is we actually sampled water runoff because they use a lot of herbicides and pesticides. And we're interested in herbicide detection because what ends up happening is the water runoff goes into the water system. Depending on how well they purify the water or not, you can use the water to water plants or you can consume the water, and there's a problem then, right? Potential health hazard. So we wanted to figure out how much they were actually adding to the system. Now, oh my goodness! Look at that, huh? Bam! So that is actually the HPLC system that's here. So the column temp was 50 degrees Celsius. We used 0.025 molar phosphoric acid and acetonitrile with 10%. And we went from 10% acetonitrile to 90% acetonitrile in 5 minutes. But one of the things that you have to keep in mind, write this down. Write down the phosphoric acid. That's important. Write this down. Or type it in your phone. Take a picture, however you want to do it. Keep track of that. It's important. All right. So we also we had a particular column that allowed us to do our separation. It's a relatively non-polar column. So we had a relatively polar solvent, but we changed polarity a little bit. We detected the analyte with a detector at 230 nanometers, so in the ultraviolet region of the spectrum. And we have some data. So we had a standard of how many different herbicides? 8. And we got pretty good separation. So what we have here is retention time on our x-axis, and we have absorbance on our y-axis.
You try again.
So we have time on our x-axis and absorbance on our y-axis. We have our different compounds that are there. The biggest one that I want you to be aware of is perchlorate. So that's the one that we're actually most worried about, quite honestly. I'm not saying that we're not worried about the other ones, but that was the initial driver of the project. So we do have an issue in terms of overlap with benzosone and 2,4-D, but all in all, this worked reasonably well. So we looked at generating calibration curves, and we made calibration curves for all of them with this particular technique. And based on different retention times for the different peaks, we're actually able to get a linear regression line, and we had R-squared values. Those of you that have an understanding of R-squared values, is an R-squared value of 0.996 good, or is that bad? It's good, right? So we want R-squared values. R-squared value ranges from 0 to 1, and this tells you how good a line fit is or not, with 1 being dead on and 0 being what in the world did you do, right? But 0.99 or better is good for most analytical work. So things worked out pretty well for the different analytes that we had there. The thing that you want to keep in mind here is we went down to about 5 part per million ish. I don't know, I can't remember if I had limits of detection here, but the that you want to keep in mind here is we're working in part per million here. With the phosphoric acid as the acid in the water-based salt. So far, so good. Anyone confused in terms of what we did? There we go. So here's the different water samples. So we got limits of detection, or at least we got detectable ranges on the order of around 0.5 part per million for chlorum. There was a lot of them that we didn't see. So what does that mean?
We're absent.
They were absent. They didn't use them, right? So, but there is some concern, right? Would you want to drink this water?
No.
No, probably not. Interesting, huh? At least the way it is. So, don't go drinking water from the runoff from the golf courses. If you're out biking and you're really, really thirsty and you see the water there, I'd say probably let it go. So, any questions here? All right, so we wanted to see if we could improve the detection limits. So we jumped ship. So we went and I phoned a friend. So I had a friend at the time at SIUE while I was here, who has a liquid chromatography system with a mass spectrometer on it. So the mass spectrometer, what it does is it works in such a way to where it actually takes the sample as it comes out of the analytical column and it ionizes the sample. So what ends up happening is with the electroscopes, that's twice now. My fault. What ends up happening is ionize it with an electrospray. And so what we do is when we ionize it with an electrospray, these ions actually travel through a quadrupole. And these poles have some voltages on it. So you have positively charged poles and negatively charged poles. And you run a sine wave through them. And it allows you to selectively filter a particular ion. And then we do it twice to improve the separation that we observe. And then it goes to an eyeball and it hits the eye and you yell ow because it hurts. Just a tender. Especially you optometry people. All right, so this is just the schematic of the system. The big key that you need to keep in mind here is we use 0.1 molar formic acid, which is up there. Okay, so you want to write down formic acid. Because that's going to play a role. Maybe. Because I need some help. You're gonna have to tell me if there's any differences or not. They use the same standards, the same everything, but they got concentrations on the order of I'd say 6 to 4 to 6 parts per billion in terms of the mass range setup, because the samples that we had, they got concentrations ranging from 8 to 42 part per billion the chlorum, and they were actually able to detect all the other herbicides. Now, my question for you is, why do we have part per billion here? And why do we have part per billion with what we did at Maryville? This is part per billion, but the other one was part per million.
Okay, well, that's 1,000 times more accurate or something.
It's not necessarily accuracy. This is much, there's a lot lower sample here. There's not as much stuff here. We did the same thing. We worked with the same column. Or did we do the same thing? We worked with, I'll tell you, we worked with the same column. Did we work with the same solvents? No, we didn't. What was different about the solvents? you quant people or you Gen Chem 2 people, is there a difference between phosphoric acid and formic acid? How do you know? Pull up AI and look and tell me if there's a difference. I don't know these things. What are you going to look for in terms of the differences between phosphoric acid and formic acid? Structure, so we can get the structure. What else? What number value can we get that's going to tell us something about the acid? pKa. So we're going to want to get pKa. How many pKa's does formic acid have? One. And what is the pKa value of formic acid? Who's got a whiteboard marker? Someone's got a whiteboard marker. All right, so does this still work?
Yes.
You can't read it, but that's okay, right? So 3.75, good enough. All right, so now we have that. Now, what's the pKa of phosphoric acid? 2.15? And is that the only pKa that they have? There's 3. Why is there 3? Because it's a trichloric acid. They put the H subscript 3 so that 3 hydrogen attack to be able to come up, right? So what's pKa 2? 7.20 and then pKa 3. 12.35. Now, we want to look these up in actual references to validate them, but I think they're pretty gosh darn close for government work. So this will give us some idea. Now, you're going to have to use AI for this one. So use your AI of choice. And what we need to do is we need to get the pKa's for these guys. Because what we want to be able to do is we want to look to see if there's a transition that's going to occur that's going to make these polar or non-polar. Yeah. So 2.3 is the pKa for this. With that in mind, how does that correlate with our choices here? This is what we had. This is formic acid. This is phosphoric acid. So we actually had very, very high concentrations with this. If the pKa's are similar, that means we're probably going to have a lot of both species present. Those of you that have worked with the Henderson-Hasselbalch equation. Oh my goodness, I have to remember that one. Do you remember that one? Yes! Zach, did your lab instructor talk about the Henderson-Hasselbalch equation at all? Probably. That was a long time ago, wasn't it? A long time ago. Yeah, it's old.
Yeah.
You know, can I still throw markers in? Thanks, Zach. All right, so my guess is, or my hypothesis is, there was a shift in polarity. Because we needed to work in a more acidic condition to get the herbicide in the right form to interact with solvent. So what ended up happening is with the lower pH, or with the higher pH, lower hydronium ion concentration, we formed the non-polar herbicide compound in the solution, and it stuck to the column and didn't go through with what happened with the mass spec analysis. So what we need to do is we need to redo the analysis with the phosphoric acid solution instead. And I feel fairly confident that that would happen. I had planned to share that hopefully one of our soon-to-be students at SIUE would be able to do that study, which is actually the same student who did this. But I found out recently, like last night at 11 PM, that he got accepted to University of Kansas. So he's not going to SIUE. So what am I gonna do?
You receive one more from you,
Yeah,
maybe an undergrad student who will do research there. You'll have a co-supervisor here and you supervise them from there.
there you go. No, I like it. Or maybe what we'll do is that.
Everybody ready here?
Zach, if things don't work out.
Yeah.
Okay, just a second. All right, so we talked about the differences, so what we need to do is, I feel comfortable saying that we would probably want to revalidate the UV system, essentially repeat it, that you can do this work, and then compare it to. I don't want to modify the method that we use for the HPLC method, I'd probably keep the same, but I would actually use this here with the LCMS, and we could potentially do GC work as well. Any questions here? I gotta look at my phone, at what time is it? 4:09, okay, so we have till. 4:30, good, plenty of time. Any questions before I jump gears? Drink spiking is a persistent issue. Commonly used. Items are roofies or GHB. Which tends to be an issue because side effects are confusion, drowsiness, amnesia, unconsciousness, blackouts, and yes, you can die from. 1,4-butanediol is a common industry chemical unregulated issue. So this is an uncontrolled compound. And when you consume it, your body metabolizes it into GHB. So your liver processes it in such a way to where in your body you actually have GHB. So if someone believes that their drink was spiked, it's possible that the only way to properly test for 1,4-butanediol is to screen the leftover remnants of their drink. So that's one of the things that we're working on. And I will tell you that there is, I know of one manufacturer in Benton. And they make a lot of it. You can get a liter of this for about $50. Is that expensive or cheap? Cheap, good. So it's well known in the drug world, but it's not necessarily well known in the forensics world. And so my goal is I want to get this out here, and I want people to be able to be aware of it, number one, and then also we'll talk about different ways to analyze for it. So what we want to be able to do at the end of the day is if there's a beverage that's there, we want to be able to screen this beverage quickly to be able to identify whether or not there's any adulterants in it or not. So I will give you a little bit of a preface here. Professor Hayes, anyone know Professor Hayes? She teaches forensic chemistry this semester. She actually works for St. Louis Metro Crime Lab, and she is the drug chemistry technical leader. Okay, she actually had a sample that she had to analyze, and it took her a long time to figure out what the adulterant was. And so the project has evolved because of her interest to come up with a way to do this quickly. So what we did is we actually have different liquors, and we would take a liquor mixer and 1,4-butanediol and put it into a sample. So this is the list of the liquors that we have. So we actually have all of these. I've actually purchased all of these. We have these in the lab, readily available to make pretend drinks that no one partakes of because they have become stock samples in the lab. So there's the different mixers that we have, and I will tell you that Mio was the actual mixers that was found in the sample that Professor Hayes had. And these are the different dosages of the 1,4-butanediol that we used. Okay, now, based on the structure of 1,4-butanediol, different components of the spectrum that you're going to see are associated with OH stretching, CH bending, and the primary alcohol is present. So I have this here mainly for the organic people.
How many of you remember that one, the spectrum?
Okay, now
Good.
the thing that I want you to be aware of here is, I actually, the blue plot is actually a plot of water and vodka that is wet. So what we did is actually put it on the ATR, so this is actually a sample of the ATR. So we just put the solution on the ATR, and that's the spectrum that we obtained in blue. So that's with water and the vodka. You have a hard time seeing the alcohol because the alcohol is interacting with the water. Water is just being a pain, right? Yeah. So what we did is we let it sit for about 18 to 20 minutes. And guess what's going to fly away? The water and the alcohol. And what's going to be left? The 1,4-butanediol. So the 1,4-butanediol is actually not very volatile. Water is somewhat volatile, right? Does water like to fly away? Unless it's really humid. Right? Ethanol is going to fly away, right? Let's see, right? So what you're left with is a solid, and I guess in this case, or very, very viscous liquid on the crystal. You actually get your measurement that's made, and that's why the peaks look a lot better. So far, so good. So what we did is we had different concentrations of the 1,4-butanediol. Things looked pretty good. You can see that concentration goes up. We can see more or better defined peaks if we have more sample present. As we go from left to right, definitely well defined. We do hit, I don't want to say it, a threshold point, but there is minimal change. But nonetheless, we do see a change. But IR is typically not used for quantitative work. Is that correct? Those who are doing quantitative analysis, anyone here to instrumental analysis? So we have some problems though. Sugar poses a problem because sugar doesn't like to fly away, does it? Okay. So with that, gotta remember where I am here. So this is using 0.125 milliliters of the 1,4-butanediol, cola, whiskey, and this is wet. So we let it dry. Things look pretty good. Or do they? This is whiskey and the 0.125 or 0.125 milliliters of the 1,4-butanediol dry as well. Our sugar problem issue is predominantly over here. And so we're not able to distinguish the 1,4-butanediol with the spectrum here. Yes, we're able to get these peaks, but the downside of these peaks on the left side of the spectrum is we're going to see similar peaks with sugar. So we're not going to be able to identify the 1,4-butanediol. So what we have to do is we have to figure out a way to get the sugar out. Okay, now with that, sugar is going to adhere to water, correct? Okay, now, how do we prevent sugar from adhering to water? And now we're going to run across some problems there. In the vial, we're going to have the sugar, the 1,4-butanediol, ethanol, and water. How are we going to get rid of or prevent the sugar from interacting with water? Is there something that we can do to prevent sugar from interacting with the water? Let me ask you this. I think this is kind of borderline between Gen Chem 1 and Gen Chem 2. Are there what are the intermolecular forces that are holding the sugar to the water? Is it hydrogen bonding? What are the predominant forces? Is there a lot of hydrogen bonding with sugar? Is there hydrogen bonding with sugar?
Actually, no, the hydrogen bonding is hydrogen bonding.
Yeah, so hydrogen bonding is ET phone home, right? FON, fluorine, oxygen, and nitrogen. So. We don't have any of those interactions, so the only intermolecular forces with the sugar is going to be. Dispersion forces, yes. So what we need to do is we need to add something to the solution to prevent those intermolecular forces from happening. And I'm going to skip to what we did. So we actually added a salt. So we added potassium carbonate. Why did we add potassium carbonate to this solution? What's going to interact with the water? The sugar or the salt? So what kind of interaction are you going to get with the salt? So it's going to be, so you're going to ion interact. The water is going to have a strong interaction with the ion's going to have a stronger interaction with the water than the sugar is going to have with the water. Because of that, the ion is going to prevent the sugar from interacting with the water, and it's going to force the sugar to precipitate out.
It's forcing the third wheel.
Yes. So it's forcing the sugar to fall out of solution. It's not going to force the 1,4-butane diol out. It's not going to force the ethanol out as much. Yes, it's going to force it out some. But which one's going to be forced out the most? The sugar, because it's the most non-polar. Is that what we want to do? Yep. So, different things that we have to worry about. We did a separation of Coke with tequila and water, dry ATR. So we're able to get our 1,4-butane diol. It's now identifiable. Yes, we do have peaks associated with the carbonate. I might consider using a different salt later, but this works well. And if it ain't broke, don't fix it. So, so I have this here because I want to show the results in greater detail. So we have vodka, water, Coke. So I have the different concentration levels for the 1,4-butane diol. So this is no salting out. Yes, you can see some components, but if I go to salting out by adding a boatload of potassium carbonate, you see more well-defined peaks. So these are definitely more well-defined. We can actually use those to identify our 1,4-butane diol. We can use these at the 1,000 weight number level to identify our 1,4-butane diol. You can see the change in the concentration as we go from the orange to the blue to the yellow. We can see that this peak gets bigger. These peaks get bigger. It's working. It's doing what we want it to do. It takes us 5 minutes. This is a whole 20-minute process to be able to get this information. Conclusions. We can identify it. Dry as opposed to wet is definitely the way to go. Residues on the diamond in the mixtures do occur. We have to make sure that we do a really good job of cleaning the diamond on the ATR FTIR. So we can use the potassium carbonate to separate the sugar and the 1,4-butane diol. This method proves to be a probable, and I would call it presumptive based on what Swig says. And so this is essentially like a governing body that comes up with methods to identify whether or not they are confirmatory or presumptive. I would say this is more presumptive because we have a multi-component mixture. Swig says that we can actually use FTIR as a confirmatory method, but because of the mixture that we have some issues, especially since we have some potential overlap. Yes. Next steps in this study, perform additive mixer tests. And we're actually going to use more real cocktails, so a lot more. So our goal is, we're actually more interested in characterizing using this, because this isn't in the literature. What ended up happening is, some people have actually used this method for other adulterants, but what they did is they characterized just using the adulterants and alcohol and water. They didn't have any of the other stuff. But when you go out and have alcoholic beverages, you add all the other stuff for flavor. It's gonna be there no matter what. So we have to keep this as real world as possible. We're gonna work with bigger sample amounts as big as we can, and we're gonna try and mimic as many drug facilitated crimes as we can. We're gonna look at all different scenarios. We're gonna see how low we can go in terms of sample size, work with big sample sizes, see how reproducible it's going to be. With that, one other thing I will say is, in regards to this as well, this is actually a bigger problem than people could believe it to be. If I actually go out drinking on occasion, and I do a very good job of making sure that I watch my drink at all times. And I will share that if you ever partake in any beverages of any sort like this, especially when you work with open cups, watch your drink. And if there's ever any doubt, it's worth your financial investment to get rid of the drink and get it more. And I'm not advocating drinking per se. If you choose to drink, I'm asking that you be careful in terms of what you do. Okay? It's very important. Even quite honestly with bottles, it's very easy. So if you have a bottle of beer, for example. Or a bottle, we could say a bottle of SEMA, which I have seen out there on occasion. So, any questions? All right, people I need to thank. So these are all different things. There's a whole group of Maryville students up here. These people up here are all former Maryville students. Let's see. Kelsey is actually teaching she's teaching down in near Bourbon, Missouri. Katie is actually working for the Missouri State Highway Patrol in Springfield. I don't know where Adam, Emily, or Emma are. Megan is at SLU. Fatty actually graduated with a master's and is working now. He's got a job somewhere. Sigma, yes. So he messaged me about 2 months ago. Chris is actually looking at getting into the PhD program at SLU. He's currently in the master's program there. I don't know where Delaney and Bailey are. Marissa graduated from Maryville, and she was the main instigator in the project up here. But Marissa, when she graduated from here, I recruited her. She actually did a year's worth of research at SIUE while she was a student here. And I recruited her for the master's program, but she said, no, I want to move to Florida to be by my fiance. I said, what were you thinking? Now she made the right choice. She has to do a fest for it. Carlos is actually at WashU. He started the herbicide runoff work. Actually, we had some high school students work on it first, but Carlos is the first Maryville student that actually worked on the herbicide project. And we collaborated with Dr. Chambers. Anyone know Dr. Chambers? And then Bren continued to work and did most of the work that we saw here. And Bren was the one that was supposed to end up going to SIUE, but for some reason he got into KU, chose KU over SIUE. So no, he made the right choice as well. Marissa, I talked about. Ethan, Aiden, Miles, and Emma are all current students at SIUE. And they are all undergraduates. Let's see, Ethan's a junior, Aiden's a senior. He might apply for our program. It's kind of up in the air. He's bounced back and forth between this medical school thing. So I don't know what he's thinking. Miles is actually going to be starting in our program in the fall. Emma is a sophomore who just started this semester and is knocking out of the park in terms of work that she's doing. And I talk about that's for Hayes. These are all SIUE folks. And then I actually got to go on a sabbatical while I was here. And these are all the people that I worked with there, and I didn't talk about any of the work that I did there, but I've actually I published quite a bit on the 5% sensor work. And we have at least one patent in the works, possibly two. So with that, I am done. Any questions?